Good afternoon, class. We are looking at chapter 3, derivatives. Here, section 3.8, differentials and linear approximation. Differentials and linear approximation. We're going to cover all of it, part 1 as well as part 2. So we cover derivatives and rates of change, derivative as a function, basic differentiation formulas, the product and quotient rule, the chain rule, derivatives of logs, and now differentials and linear approximations. Here's the synopsis of that, which will be discussed shortly. We have various formulas, as you can see here, for differentiations from the basics to the product rule, quotient rule, power rule, extended power rule, exponentials, composite function resulting in the chain rule, as well as logs. Needless to say, we also have the definition. We looked at logarithmic properties. In the case where b is positive and b is not equal to 1, x equals b to the power of y is y equals log x base b. Notice they have the same exponent and the same base b. And over here, log x base b equals y, with this arrow tells us b to the power of y equals x. As long as we can go from one format to the next, and that's the case in the case of a general, we can come up with all the properties. Log 1 with any base b is 0. Log b base b is 1 when the base and the argument are the same. The answer is 1. Log base b of b to the power of x is x. Notice all those three follow this arrow. And these two refer to the fact that the two functions, logarithmic functions and exponential functions, are inverse functions. Log base b xy is log x base b plus log y base b. This is a product rule. Log base b of x over y is log x base b minus log y base b. This is known as the quotient rule. Log base b of x to the power of n is n log x base b. That means that's a power rule. When we write log and there is no base, that means the base is 10. That means you're dealing with a common log. Y equals log x means 10 to the power of y equals x. We should be able to transition from these general properties to a specific one with the base 10. For example, we drop the base in all cases. Log 1, I'm looking at the first one, 5 and 6, 7 are just dropping the base. This one becomes log 10 because we know the base is 10 and the rest of them follow. In the case of a natural log, when we write y equals ln x, that means log x base e. Do not write that. This means e to the power of y equals x. And again, the transition from the general to a specific case, natural log. So just for number 1, 5, 6, 7, instead of log, use ln. And number 2, since the base is e, you have to use the argument e, and the rest of them follow. Logarithmic functions, exponential functions are inverse functions, and therefore, if you graph them on the same set of axes, symmetric with respect to the line y equals x. Change of base formula says log x base b is log x over log b with any base, such as a. So we choose common log or natural log. This one, I'm going to start with this point first, which refers to this point. This point has coordinates 1, 0. Then x is less than 0. When x is between 0 and 1, ln x is less than 0. When x is larger than 1, ln x is larger than 0. The derivative of ln x is 1 over x. If it's ln of g of x, we flip it over, and this is by the chain rule times g prime. And if the base is not e, that means not a natural log, we tag along 1 over ln b. Of course, if it's f of x, log base b of f of x, 1 over f of x, f prime of x by the chain rule, 1 over ln b by the change of base formula. And now the new stuff, 3.8 differentials and linear approximation. Here's the definition for y equals f of x. We define dx called the differential of x by dx or delta x. So if you look at this curve, and we pick 2 points as we go from P to Q, we cover this distance, which is called delta x or dx, or BP equals DC. This distance is delta x, also dx. They are identical. dy, called the differential of y, is equal to f prime of x dx. To make sure we understand this, we know f prime is dy dx. If you treat this as a fraction, the cross product gives you dy. Now, as far as the graph is concerned, we go from point P to point Q. Run is delta x dx or BP. But look at the rise. For the curve, this distance is f of x plus f of x plus delta x. This distance is f of x. So delta y is precisely this distance of BQ. If you draw a tangent line at the first point P, their run is identical, delta x dx BP. But the rise, this dy is the rise along the tangent line. dy equals AB. Delta y equals BQ. They are not the same. Delta y or BQ, we call this point B, call this point Q, BQ, is this distance, f of x plus delta x, or CQ, minus this distance, f of x or dP. And therefore, delta x is precisely f of x plus delta x minus f of x. We can replace delta y by dy for a function f which is a continuous and differentiable function with a small delta x if delta y is difficult to evaluate. Again, for the sake of illustration, delta y and dy, they have a huge difference. That's really normally not the case. The point is, delta y is equal to dy? No. Can we replace the delta y by an approximation of dy? The smaller this distance delta x, the better this approximation. So f prime of x is dy dx. Can be approximated by delta y over delta x, and therefore delta y can be approximated by f prime of x delta x or dx. In other words, delta y and dy, we take them to be the same. Now, delta y or BQ is precisely f of x plus delta x minus f of x. So if you want to solve for f of x plus delta x, you move that to the other side, f of x plus delta y. We said f prime is dy dx, dy is f prime of x dx. So this f of x plus delta x would be f of x plus dy, or approximation, replace it by dy. That's all there is to it. This is known as the differentials. If you draw this tangent line at this point, this tangent line has an equation. We call it L of x. It's the linearization. So take a look. Linearization refers to finding the tangent line at some point A, for example, here. Using the point slope, y minus y1 equals m times x minus x of 1, move the y1, replace the m with f prime of a, x of 1 with a, and y sub 1 with f of a. It gives this formula, or L of x. Please understand, just use the point slope. It's very simple. Okay. And the idea is that for points, for point P, functional value using the curve or the tangent line makes no difference. In other words, at A, f of A or L of A result in the same thing because the point belongs to both of them. However, nearby, they are not the same, but sometimes if the point is close to this, close to A, then we can approximate it using the line. And that gives you the same result as these differentials. Let's look at some examples. So f of x is 4x cubed minus 3x. We want to find dy and delta y. To find dy, just ignore it, find f prime of x, which is dy dx. So we are here, which makes it 12x squared minus 3. So what is dy? Exactly the same thing, times dx. Exactly the same thing, times dx. So that's dy, and since we want to evaluate it when x is 3, delta x is 0.2, we're going to put in x equals 3, dx or delta x is 0.2. Let's so this becomes elementary algebra. We are evaluating this, and this is 9 times 12 is 108 minus 3 is 105 times 0.2. 2 times 105 is 210. 10 cancels out one decimal. 21. We are done. Delta y is f of x plus delta x. That means f of 3.2 minus f of x. That means f of 3. That's the meaning of it, everybody. So plug in. Into this goes 3.2. That means 4 times 3.2 cubed minus 3 times 3.2. And then minus f of 3, plug in 3. You put it into a calculator to evaluate this. Or you can multiply 3.2 by itself. You can do it by hand. Either way is fine. So this gives us 121.472. This gives us 99. The difference is 22.472. Now, the idea is dy and delta y are close, and they are close. However, one might say, well, they're not close enough, and you're right, they're not. Because the smaller this number compared to the choice of x, the better this approximation. For example, if this was 0.1, would be a lot better. If it's 0.01, it's almost identical. Okay. So I hope it's clear to everybody as to what's going on here. We want to find dy, and as I've mentioned before, you want to find dy, ignore it. Find f prime of x, which means you are using the product rule. F times g, f prime is 1. So we are looking at, let me just do this, everybody. F prime G plus G prime F. That's what we are looking for. So F prime is 1 times G4 minus X cubed plus G prime. We want to differentiate this. We get 3 times 4 minus X squared times the derivative of the inside, negative 1 times F, which is X. So I'm going to write at top of it F prime G plus G prime F. That's it. So first, let's simplify this by taking the common factor of 4 minus X squared out. So this gives you 4 minus X, and this gives you positive 3 minus 1 on X, which means minus 3X. And so this doesn't change. This one, 4 minus these two combine into negative 4X. And we can take the negative 4 out or 4 out. It makes no difference, but either way. So if you take the negative 4 out, you get X minus 1, and you put that in front. And that is your dy, dx, not dy. That is your f prime of x. So what is dy? The same thing, times dx. The same thing, times dx. That's all there is to it. And that's extremely important to understand. There's really not much to that. You differentiate, and then you tag along dx. You call it dy dx. That's all. It's very straightforward, everybody. Now, all you have to do, plug in and evaluate. What do you plug in? X is 5, dx or delta x is 0.1. Let's just plug it, that's all. So this is negative 1, this is positive 4. You square the negative 1, you get positive 1. So it has no effect. 1 times any number is itself. So you're multiplying negative 4 by positive 1, makes no difference, times positive 4, negative 16, times 0.1, negative 1.6, and you're done. Okay, it's that simple. Now let's do delta y. Delta y is precisely f of x plus delta x minus f of x, which means in this case, f of 5.1 minus f of 5. So you go back to the original function and plug in 5.1, which makes it 5.1 times 4 minus 5.1 cubed minus, and you plug in 5. 5 times 4 minus 5 cubed. Put it into a calculator. This one doesn't need a calculator. This is negative 1 cubed is negative 1 times this becomes positive 5. So this one, you can put it into a calculator, and the result is negative 1.7881. Fairly close to dy, and the smaller this number, the closer the two values. We are going to move on. Applications. The radius of a blood vessel is 1.4 millimeters. A drug causes the radius to change to 1.3 millimeters. Use differentials to find the approximate change in the area of a cross-section of the vessel. Cross-section is in a circular shape, and we should know the area is pi r squared. So we should have that information, class. So we have the radius, and it's going to shrink. Originally, this is the radius, and it's going to shrink because of the medication. This is R, this is the new R, and the difference is dr or delta R. So R is 1.4 millimeters. dr is negative 0.1 because it's 1.3 minus 1.4, negative 0.1 millimeters squared. And we should know the area is pi r squared. And since they are asking for an approximation in the change in the area, they are asking for dA. In other words, this shaded region, they want us to approximate it. So reminding you that we said when f prime of x is dy dx, dy is f prime of x dx. Now we're going to say a prime of r because we have a different variable. The independent variable in this case is r, no longer x, is dA dr, and we want dA, which is the product of these two. And going back here, f prime is dy dx, dy is the product of these two, and now dA is the product of a prime of r dr. And so we are going to find a prime of r, or differentiate this with respect to r. And pi is a number. So a or pi r squared is dA dr. Pi times what? Differentiate r squared to r, which makes it 2 pi r. So this is dA dr. This is a prime of r. This is not dA. dA is the same thing. Times dr. So you replace the r with 1.4 and dr with negative 0.1. You know 2 times 1.4 is 2.8. This makes it negative 0.28 times pi. This is precise. And again, you can put it into a calculator. Please do not use 3.14 for pi. And that gives you negative 0.8796. Units for dA is the units of the area, millimeters squared. Negative means what type of a change? It's decreasing. So the cross section, the area of a cross section is decreasing. And if you mention decreasing, you don't write the negative by this much. Now, what would be the exact change? That's called delta A. The exact change is to find the area of the two circles. The difference is the answer. The inner circle, the smaller one, has the radius of 1.3. So pi r squared, pi times 1.3 squared. The larger one has a radius of 1.4. So pi r squared, pi times 1.4 squared. I've taken the pi out as a common factor. And look at this answer and keeping it with pi, how close they are, negative 0.27 pi millimeters squared. This is the exact answer, delta A. This is an approximation using the differentials. So it's pretty straightforward, everybody. Let's move on. A bacterial colony has a population of P of t equals 20t over 10 plus t squared in millions. T hours after a nutrient is introduced, use differentials to approximate the change from T equals 2 to T equals 2.4 hours. You want to approximate the change in population. So what is given? T is 2, delta T or dt is 2.4 minus 2 or 0.4, and we want dp. In other words, if you look at this one, class, remember dy is f prime of x dx. Let's discuss f prime of x. So we know f prime of x is dy dx. Therefore, given p of a t, p prime of t is dp dt. Just write the formula. I want you to relate to that. So over here, we said dy is f prime of x dx. Over here, we're going to say dp is p prime of t dt, which means you need to find p prime of t or dp dt using the quotient rule. So we are going to use the quotient rule. I'm going to call it f over g. And so we are going to differentiate everybody. So f prime, the derivative of the numerator is 20 times g, just write times 10 plus t squared, minus g prime, the derivative of the bottom is 2t minus 2t times f times the top, 20t, and then over g squared, just write this in a parentheses and square it, and we're done with the differentiation. We are going to combine like terms by distributing first as follows. This is 200 plus 20t squared minus 40t squared. Just combine these two into negative 20t squared. And that's p prime of t. So what is dp? Multiply the same thing times dt. So f prime of x dx. That's simple, everybody. And so now replace the t with a 2 and dt with 0.4. We are going to evaluate it. We're going to plug in. We get 200 minus 20 times 2 squared over 10 plus 2 squared. Quantity squared times 0.4. You can use a calculator, but just to give you an idea, this is 4, everybody. So you have 200 minus 4 times 20, which is 80. And so this whole thing becomes 120. This is 4. So you have 14 squared. This whole thing is 196. And when you put it into a calculator times 0.4 gives you 0.245 and millions of bacteria, which means 245,000 bacteria. That's the meaning of it. I need this, so let's. What is the exact change? Delta P. F of x plus delta x minus f of x. So f of 2.4 minus f of 2. In this case, P of 2.4 minus P of 2. You put it into this 2.4, this is elementary algebra, gives you a number. You put in 2, gives you a number. The difference, 0.189 millions means 189,000. They're close, but the discrepancy is because if you look at dt 0.4 compared to t is very large. It should be small, like 0.1 or 0.01, and then it becomes a very good approximation. That's the idea. So again, the better, the closer the smaller the choice of dt to the choice of t, the closer the two values. Okay, that's the idea behind approximation. Use differentials to approximate 51 squared. In fact, I'm going to use differentials and I'm going to use linearization as well. First and foremost, you need a function. What function? Well, read the question. We want to approximate 51 squared. So the function that you need is the operation that is taking place. We are squaring 51. So f of x is 51. The number is 51 squared. F of x is x squared. So how do you find this function? Look at the operation that is being taken place. Number two, choose a number x close to 51 for which squaring is easy to compute. I hope everybody knows the answer is 50 because everybody knows 50 squared is 2500. Also, I want to remind you how this was actually calculated using elementary algebra and identities. If you recall, they said, okay, if you want to calculate this, write it in this fashion and use a plus b quantity squared, which is a squared plus 2ab plus b squared, of course, fairly fast in your head. So this is 50 squared plus 2 times 50 times 1 plus 1 squared. 50 squared is 2500. 2 times 50 is 100. We get 26 over. So the exact answer can be done in your head in a split second. But we want to use the differential to approximate that. Again, to recap, we need a function. Look at the operation. We need a number closest to that that does that operation. In this case, 50 gives you 2500. So what is your delta x? It's important to understand in this case, delta x, we want to go from the easy number 50 to 51. It's going to go up by 1. So 51 minus 50 equals 1, and that's your delta x. Now, please note, if we want it for the, I don't know, 8 squared, then delta x or dx would be 48 minus 50 equals -2. What does it mean? I may not know what's 51 squared, but it should be larger than 50 squared. I may not know what's 48 squared, but it must be less than that because this is negative. So this is positive. That means it has to be larger. Negative means smaller. So we want f of x plus delta x. And we know f of x plus delta x is f of x plus delta y, but it can be approximated by this. So it's f of x plus dy. An approximation because we are using differential to do so. So we have f of x, but we don't have dy. To find dy, first we find f prime of x, which is dy dx, which is 2x. And then dy is the same thing times the x, 2x dx. And so the function that we have is x squared, and we have it. And the dy we calculated to be 2x dx. So we want to evaluate this piece. And to do so, we want 51 squared, or f of 51, or f of 50 plus 1. This is your x, this is your delta x. So we are going to put this into this expression. We get 50 squared plus 2 times 50 times 1. This is 100, this is 2500. They add up to 2600. And as I mentioned, The actual value is 2601, 2601. They're extremely close. And the reason is very simple. Delta x compared to the choice of x is very small. That's why the approximation is really good. Now, let me erase this, and I want to look at the linearization. Remember, linearization simply put means find the tangent line. So I wouldn't memorize this formula. I'm going to stick with the good old elementary algebra. Point slope, y minus y1 equals m times x minus x sub 1. So I need to find the tangent line for the function f of x equals x squared at what point? At x equals 50. So what do I need? I need the pair. The pair is 50 and 2500. I need the slope, and I put the 50 into f prime. I get 100. So find L of x, that means the tangent line. At this pair, you put the 50 into the original function, gives you the pair, and the slope is, you put the 50 into f prime of x. So again, you'd have to memorize that. Y minus y1, that means y minus 2500, equals m 100. X minus x sub 1, x minus 50. And class, this is 100x, this is minus 5, and we have 1, 2, 3 zeros, and you move this one, you make it positive 2500, and these two, we end up with L of x equals 100x minus 2500. And now, if you plug in 51, because you want 51 squared, you get exactly the same number that you got here. Differentials and linearization must give you exactly the same answer. Otherwise, we made a mistake, because in essence, both of them do the same thing, class, okay? Use differential to approximate square root of 27. Same thing, we need a function. What operation? Square root of 27. Square root of x. Number 2, choose a number x close to 27 for which the square root is easy to compute. Of course, 25, because we should know square root of 25 is 5. So the choice, the closest number to 27 is 25. So what is delta x? Well, we want to go from 25 to 27, it's going up by 2. So 27 minus 25 is delta x, or dx, or 2. So f of x plus delta x is precisely f of x plus delta y, but we're going to approximate it with f of x plus dy. So we need the function is square root of x, but we don't have dy, and that means we are going to differentiate. To do that, we change the x, square root of x, to x to the power 1/2. Then f prime is 1/2, x to the power 1/2 minus 1, or negative 1/2, which makes it 1/2 square root of x. And dy is the same thing, times dx, times dx. That's how you go from f prime to dy times dx. So now we have both of it. We have the function, which is square root of x, and we have dy, which is 1 over 2 square root of x dx. So pretty straightforward, everybody. Okay, makes sense? All right, we want square root of 27. That means we want f of 27. That means f of 25 plus 2. That means replace the x with 25 and the x with 2. That's the meaning of it. Let's do that. Replace the x with 25, dx with 2. And we know that this is 5, this is 5. These two cancel each other. 5 plus 1/5. 5 and 1/5. 5.2. We are done. Just to show you that the calculated result, everybody, the calculated result for a matter of comparison is very close. In fact, if you were to stop here, you had to change it to 2. Okay, so that gives you an idea. Again, I want to look at the tangent line and reminding you of the linearization that was discussed previously, and the tangent line for f of x equals square root of x at x equals 25. That's important to know. Tangent line at what is the function and at what point? 25. So you plug in 25, you get 5. So the pair is 25, 5. You put this into f prime, that gives you this slope. If I put 25 here, I get 5. 1 over 2 times 5. 1 over 2 times 5. 1 over 10. So L of x is a question mark. The pair is 25 square root of 25, 5. F prime of 25 is this slope, which is 1 over 10. And I'm going to go with elementary algebra. I don't want you to memorize that. You don't have to. Y minus y1. That means y minus 5 equals m 1 over 10 times x minus x of 1, x minus 25. And if you distribute, this becomes 1 over 10 times x minus 25 over 10. 25 over 10 class 25 over 10. Both of them are divisible by 5, same as 5 halves. And now I'm going to move the negative 5 and make it plus 5. Plus 5 and negative 5 halves gives us plus 5 halves. Now, if I plug in 27, class, if you plug in 27, 27 over 10 plus 5 halves, add them up, you'll see it becomes 5 and 1/5 or 5.2, which is exactly what we have here. So I highly recommend you do that. Okay. .2 or 5.5. That's the idea. Okay, everyone. So make sure you do this to convince yourself that you've come up with the correct answer. So linearization and tangent line must and they will give you the same answer, everybody. Linearization and differentials, this process, they must give you the same answer. And they always do. Measurement error. In a manufacturing process, ball bearing must be made with a radius of 0.6 millimeters with a maximum error of plus minus 0.15 millimeters. Use differentials to estimate the maximum error in the volume of the ball bearing. So each one of those is a ball bearing. They are in the shape of a sphere. And they have this radius of 0.6, or they must have the radius of 0.6. If it's a little bit more or less, it still works. If it's more or less by this amount, 0.15. So what happens if it's smaller? It still works, but if it's smaller more than that, it will fall off. It will not work. If it's a little bit more, that means more than that. In other words, 0.6 minus 0.015 for the smaller one is 0.585, it still works. If it's larger than that, the radius is 0.615, it still works, but if it's larger than that, it gets stuck. That's the idea behind that. Use differentials to estimate the maximum error in the volume of the ball bearing. So R is 0.6, delta R or dr is 0.015, and we should know the volume is 4/3 power cubed, and we want dV. So again, very straightforward. That shouldn't be a problem, everybody. Okay, I hope everybody is okay with that. Well, those are the given. The volume is 4/3 pi r cubed, and we want dV. And to find dV, first and foremost, we are going to find V prime of R, or dV dr, which means 4/3 pi, because this is a number. It's not going to go away. Now we just differentiate R cubed, 3R squared, and cancel out the 3 from the top and the bottom. You have 4 pi R squared. So you're done with dV dr, everybody. But what is dV? dy is f prime times dx. dV is the same thing times dr. We're going to plug in. So dV is 4 pi r, which is 0.6 squared, times dr, which is plus minus 0.015. Now you have to put this into a calculator, everybody, to evaluate it. Gives you plus minus 0.0216 pi. Please do not change the pi to 3.14, okay? Just put it into a calculator, because a lot more than that, and it gives you, if you want an approximation of that, plus minus 0.0678584. Units are the units of the volume. So this was in millimeters. This is millimeters cubed. So always pay attention to the proper units. As far as the exact change is concerned, we are talking about delta V. What is the exact change? Well, calculate, as I mentioned, the radius for the smaller one and for the larger one. The smaller one would be 0.585. the larger one would be 0.615 because you are going to add and subtract this number from this. So now 4/3 pi r cubed. If you plug in 0.6, that gives you the area that you want to have. If you plug in 0.615, that gives you the area when it's large, the volume which is larger, volume, not the area. So subtract the two, that gives you the upper, limit. And if you use the smaller one, that means 0.6 minus 0.015, that means 0.585 cubed into this. And now the difference between that and when it's 0.6, as far as the volume, that gives you the smaller one on the positive side, on the negative side. Those would be exact values. This is the approximation, and I highly recommend you do that. You see how close they are. They are extremely close. And the reason they are extremely close, because this is fairly small compared to the choice of radius being 0.6 millimeters.